For over a century, physicists have been intrigued by the idea of black holes, with the concept gaining traction around 1916. These cosmic anomalies are among the most captivating and enigmatic phenomena we know, sitting at the intersection of vast gravitational forces and a peculiar invisibility to our understanding. A black hole potentially weighing as much as 2 to 4 million times the mass of our Sun remains a mysterious presence in the cosmos. Despite decades of intense research, our understanding has expanded from almost no knowledge to piecing together more details, with even more discoveries being made recently. A breakthrough by Michio Kaku has revealed startling insights about the interior of black holes, which may challenge our long-held assumptions and offer new perspectives on the nature of these celestial bodies. This new information opens doors to deeper explorations into what might have been overlooked until now. Join us as we venture further into the fascinating world of black holes and uncover what's hidden within the universe's vast and inspiring expanse. Before we delve into the latest findings by Kaku, it's essential to revisit the basic understanding of black holes. While most of us have at least a general sense of what a black hole is, there are still some key elements that remain unclear. In 1916, Albert Einstein's groundbreaking theory of general relativity predicted the existence of black holes. At that time, the notion was purely theoretical. It wasn't until about 50 years later that evidence was discovered confirming that black holes are real objects in space. This revelation came in the 1960s during studies of the star Cygnus X1, a luminous celestial body emitting X-rays. Observations showed that these X-rays were not just randomly moving but were being drawn into a dense, invisible mass. This mass, later identified as a black hole, changed our perception of the cosmos. The discovery was monumental, as it proved that black holes were not figments of Einstein's imagination but tangible, elusive entities that warranted further investigation. Following this groundbreaking discovery, scientists worldwide began a global quest to uncover more about black holes. Their efforts led to the realization that the Milky Way alone may host around 100 million black holes. However, due to the challenges in detecting them, this estimate remains imprecise. Even though black holes are incredibly difficult to pinpoint, scientists believe that millions of these massive entities are hidden within our galaxy, making it even more crucial to understand them. Black holes exert such immense gravitational forces that anything entering their domain is squeezed into a singularity, a point where the laws of physics as we know them cease to function. In simpler terms, black holes are like gigantic vacuum cleaners pulling everything into them. One of the most terrifying aspects of studying black holes is that if someone were to fall into one, they would gradually stretch out and become a singularity, their body torn apart by the intense gravitational forces before the point of total destruction. It's best to avoid getting too close to one, though they are scattered across the universe. Despite the nearest black hole being nearly 500 light-years away, the proximity still raises legitimate concerns. The first image of a black hole. In 2021, scientists achieved a historic milestone by capturing the first clear image of a black hole, the M87 black hole. This achievement was the result of numerous nights spent taking photos and aligning them to create a single cohesive image. As more data was gathered, researchers were able to discern that black holes consist of 3 distinct layers, contrary to the common misconception that they are just endless voids. The event horizon. This marks the point beyond which nothing can escape. Once something crosses this boundary, it is inevitably drawn toward the black hole. The photon sphere, here light itself, gets trapped, unable to escape due to the powerful gravitational forces at play. The singularity, all matter is compressed into an infinitely small point where the very fabric of reality collapses and all known laws of physics break down. The complexity of black holes. Each black hole is unique in its own right. While they follow the general 3-layer structure, their behavior can vary significantly. This makes them particularly challenging to study, as conventional scientific methods don't apply. Scientists have no choice but to investigate these anomalies through indirect means, such as observing the radiation emitted from them or analyzing the gas and dust swirling around them. Sending a probe directly into a black hole is futile, as anything that crosses the event horizon is inevitably pulled toward the singularity, where it is crushed into nothingness. Adding to the complexity of black hole research is the fact that no 2 black holes are identical. When studying them, we must account for the breakdown of physics as we know it. Theories about the origins of black holes suggest that they may form when massive stars collapse in on themselves. The formation of black holes. As a star burns through its fuel, it can no longer produce enough energy to counterbalance the inward pull of gravity, leading to its eventual collapse into a black hole. If the star is massive enough, this process continues until the collapsing matter becomes a singularity. To further understand the nature of black holes, NASA scientists turned their attention to the center of the universe, particularly the M87 galaxy. There they observed a powerful whirlpool of hydrogen gas spinning at mind-boggling speeds of 1.2 million miles per hour. The centrifugal force should have caused this gas to fly apart, but instead it remained intact, suggesting the presence of a massive object at the center, likely a black hole. Wormholes and space-time. In 1963, New Zealand mathematician Roy Kerr used Einstein's equations to describe the behavior of rotating black holes. He argued that rather than collapsing into a point, a rotating black hole forms a thin ring-like structure known as the ergosphere. This rotating disk of matter is key to understanding the breakdown of physical laws near black holes. Kerr's model also predicted the existence of an Einstein-Rosen bridge, a theoretical wormhole that could provide a shortcut through space-time connecting distant regions of the universe or even parallel universes. Although wormholes are a theoretical concept and no direct evidence of them exists, they are a natural consequence of general relativity. However, wormholes are inherently unstable, meaning they would collapse quickly if created. Critics argue that Einstein's equations, while useful for understanding gravity, do not account for the quantum forces that govern radiation and subatomic particles. To truly understand black holes and wormholes, a new theory is needed, one that unifies gravity with quantum mechanics. This theory of everything is a quest that many physicists, including M. Kaku, have pursued for years. One promising candidate for this theory is superstring theory, which suggests that subatomic particles are actually tiny vibrating strings. The theory proposes that these strings create the universe's fabric, explaining not only gravity but also the phenomena surrounding black holes and wormholes. However, superstring theory also requires the existence of extra dimensions of spacetime, which are so small that they are impossible to detect with current technology. Despite the challenges, the pursuit of understanding black holes, wormholes, and the fabric of spacetime continues to captivate scientists. With each new discovery, we inch closer to unraveling the mysteries of these cosmic giants. Whether through the study of gravitational waves, advancements in imaging technology, or the development of new theories, black holes continue to fascinate both scientists and the general public. As we explore the universe's most extreme and enigmatic objects, we confront fundamental questions about the nature of space-time and existence itself. In doing so, we may be on the brink of unlocking some of the greatest secrets of the universe, perhaps even finding answers to questions that have eluded humanity for millennia. The future of black hole research. The study of black holes has entered an exciting era driven by advancements in technology, observational techniques, and theoretical physics. While we have made significant progress in understanding their nature, many mysteries remain. Future research aims to answer critical questions such as: to tackle these questions, scientists are relying on new observational tools, cutting-edge physics, and collaborations across multiple disciplines. Advancements in observational techniques. One of the most promising developments in black hole research is the expansion of gravitational wave astronomy. Since the first detection of gravitational waves by LIGO, Laser Interferometer Gravitational Wave Observatory, in 2015, scientists have been able to observe collisions between black holes, offering a completely new way to study these objects. The ability to hear black holes merging has provided crucial insights into their masses, spin rates, and frequency of occurrence. Future gravitational wave observatories, such as the upcoming Laser Interferometer Space Antenna, LISA, will allow for even more precise measurements and could detect signals from smaller black holes or those interacting with other cosmic objects. In addition to gravitational waves, telescopes like the Event Horizon Telescope, EHT, are being upgraded to provide sharper images of black holes. The EHT's first image of the M87 black hole was a groundbreaking achievement, and future observations could capture even more details such as the movement of matter near the event horizon. Another exciting possibility is the development of X-ray telescopes with higher resolution, such as NASA's RISM mission and the upcoming Lynx X-ray Observatory. These instruments will allow scientists to study how matter behaves as it spirals into a black hole, providing a deeper understanding of the physics governing these extreme environments. The black hole information paradox. One of the greatest unresolved puzzles in theoretical physics is the black hole information paradox. According to classical physics, anything that falls into a black hole should be lost forever. However, quantum mechanics suggests that information cannot be destroyed. This contradiction has puzzled physicists for decades. Stephen Hawking famously proposed that black holes emit radiation now known as Hawking radiation and eventually evaporate over time. However, if black holes disappear completely, what happens to the information that fell inside them? Does it escape in some unknown form, or is it truly lost? New theoretical breakthroughs suggest that black holes may retain information in subtle ways. Some physicists propose that information could be encoded in the soft air hypothesis, where quantum effects store data on the event horizon. Others believe that the key to solving the paradox lies in quantum gravity, a yet-to-be-discovered theory that unifies Einstein's relativity with quantum mechanics. The study of black holes is closely tied to the search for a theory of everything, a single framework that unifies all fundamental forces of nature, including gravity. Since general relativity and quantum mechanics are currently incompatible, physicists are exploring various approaches to bridge this gap.